To begin exploring the carbonyl components, it's of course important to first have a look at the quantum mechanical description of these bonds. And carbonyl components are generally components that have a carbon-oxygen double bond. And as we've seen for the alkene components, which also featured a carbon-carbon double bond, this double bond in this case is also made up of one sigma bond and one pi bond. The bond angles around the central carbon atom with the two organic moieties and the important oxygen atom here are again 120 degrees, as we would expect for an sp2 hybridized carbon atom. And as we've seen numerous times already for the sp2 hybridized carbon atom, we have one p orbital sticking out here, and this lonely p orbital then forms together with another p orbital from the oxygen this second bond here, and this is the pi bond that we've seen. So it's exactly the same as we've seen already for the alkenes. So we have one sigma bond along the carbon-oxygen axis, and then we have pi electron density above and below the oxygen, the carbon-oxygen layer. So there's electron density above and below. And as we've also seen already, all these substituents, like for example here in this case the simplest carbonyl component, the formaldehyde, or the more systematic name, the methanol, all of these four atoms are in one plane, and again this electron density here is accessible. Something that is important to realize here is that we can draw mesomeric resonance structures, and in this case the oxygen is much more electronegative than the carbon atom. So the oxygen atom pulls a little bit more on this electron density on this pi bond, so we can formulate the following resonance structure where our oxygen atom gets a negative charge and the carbon atom has a positive charge. And from that we can clearly deduce that our oxygen atom here in carbonyl components can act as a nucleophile, where our carbon atom here can act as an electrophile because it's slightly positively charged.